So we've learned how to write rate laws and determine the reaction order from a set of experimental data. We also need to be able to determine the overall reaction order from a graph, from a set of data that's been graphed depending on the different plots of the graph. So let's talk about a first order reaction. Okay. So a first order reaction would be an overall of where x plus y equals 1. First order overall. So an example could just be reactant A turns into a product. All right? So if that occurs, we are going to get a plot by writing the relationship between the rate and the rate law. So we know the rate is equal to the negative change in concentration of A over change in time. And we know that the rate law tells us that rate equals K times the concentration of A. And since this is a first order reaction, we know it's to the 1. So since both of these equations have rate in them, we can set them equal to each other. Negative delta A over delta T equals K times the concentration of A. So what we're developing here is we're developing what is the relationship between the rate and the concentration. Whereas this side is essentially our rate, and what exact impact does concentration have on the rate? Well, through some calculus, if we integrate here, we can determine that the natural log of the concentration of A sub t, meaning at any given time, divided by the concentration of N sub O, the way we would say this is, A sub O is equal to negative KT. Then we know with our log rules, if we divide logs, that's the same thing as subtracting them. So this turns into natural log concentration of A sub t minus natural log of concentration of A sub O equal to negative KT. If we flip this over, we add natural log of A sub O to both sides, we're left with natural log of A sub t is equal to negative KT plus natural log of A sub O, A naught. What does this A sub O mean? This means the initial concentration, so the concentration of reactant that you started out with. Whereas this is the concentration at any given time. So at like 20 seconds, 30 seconds, 40 seconds, it doesn't matter. Well, why is this so powerful? What this does is it gives us a direct linear relationship between the concentration of a substance at any given time and the rate constant. Because if we think about this as a y equals mx plus b, if we take natural log of A sub t as our y, k to be our m, x to be our t, and this to be our b, and we plot a graph with these values on the x and y axis, we can always figure out the rate constant. So y, if we plot natural log of A sub t versus t, we'll get a linear graph where the slope is equal to negative k. So what you need to know for a first order reaction, this is all the background of how this is derived. What you need to know for a first order reaction is if you have a graph, this is what we're going to practice in class, if you have a graph that has natural log of A sub t on the y-axis and t on the x-axis, you know that this is a first order reaction, and you know this is the equation that relates those variables. So you need to kind of recognize these three pieces. together. What about in a second order reaction? I'm not going to do the derivation of figuring out the equation, but for a second order reaction, for example, A turns into products, and we have an example of like rate, if it's second order, equals K times the concentration of A squared. That would be second order overall. The equation that we would end up with after the kind of calculus derivations is the change in concentration of A, 1 over that, is equal to KT plus 1 over the concentration of A sub naught, meaning the concentration of A that we started with. So let's think of this again from our y equals mx plus b standard perspective. If we plot this on the y-axis and this on the x-axis, our slope, m, of that line is going to be the rate constant for this second order reaction. So again, if we take 1 over change in concentration of A sub t versus time, we'll get K with a positive slope. We'll get a line with a positive slope, and that slope is equal to K, the rate constant. So what you need to be able to recognize here is if you have this graph that has 1 over A sub t on the y-axis and t on the x-axis, this equation, you know that it's second order. You know that a graph like this is for a second order reaction and the slope of the line is K. The last one we need to know is a zero order reaction. So an example of this would be rate equals, for like A turning into products, rate equals K times A to the 0. Well, we know anything to the 0 is 1, so this is really just rate equals K. So the derivation of this, we would get an equation that says concentration of A sub t equals negative KT plus A sub naught. Again, if we apply y equals mx plus b, y equals mx plus b, we see that if we plot A sub t on the y-axis and t on the x-axis, the negative slope of that line will be equal to our rate constant. So here's our line with the slope is equal to negative K. So again, what you need to be able to recognize is if you have a graph with a plot of A sub t on the y-axis on t on the x, and it's a negative line, you know right away that this should say 0